Okay, so I'm starting this lecture today with a basic diagram. Please keep this diagram in mind that I hope this concept is clear to you guys. But still, I'm explaining that suppose we have a core here. The core is C1, and each core has a L1 cache. L1 cache normally divided into instruction and data, but I'm showing only an L1 cache here. And there is a L2 cache. L2 cache we will call it last level cache here. So it is LLC. So how it works when a core request for a block, first we will search it in L1, and if the block is not in L1, then we search it in L2. And if the block is not in L2, then we have to go to main memory, bring the block first to LLC, and then from LLC we move the block to L1, and from L1 we go to C1 to the core. This is how it works. So this concept you have to understand. Another concept is modern days, instead of one core and one setup, it may be possible that there is one more core here, C2 and core 2. It has also one L1 cache, its own private L1 cache. And now in this case, this setup, both are sharing this last level cache or the L2 cache. Normally, this cache L1, L2, all caches are actually set associative cache. So you can consider all these caches. There are three caches here, two L1 and one LLC. All these three caches are of this structure, set associative cache. I hope I have already explained you what is called set associative cache. So all these things you have to keep in your mind throughout this tutorial, that this is the setup, that there can be multiple ports, and there can be private caches like this L1. There may be two level of private caches like L1, L2 can be private, and in that case L3 will be your last level cache. Normally Champsim setup is like this. The simulator has, I think, three level of caches are there. All the core has private L1 and L2 cache, and then there is a shared last level cache LLC, and all the caches are set associative cache. As I'm showing here, there are multiple sets here. And I think in first lecture I've explained you, then in set associative case you have to fix a particular set first, and then based on set index, and then inside in this set you can place the block in anywhere. And if the set is full, you have to replace some block, and then you have to use replacement policy. All these things you have to understand. And one more thing is, since this set associative cache, this cache looks like a 2D array. So when we simulate it, every simulator simulate it as a 2D array. Maybe they will use vector of vector, but a vector of vector is also almost like a 2D array, right? So they will simulate it using a 2D array kind of thing. So the next question is, why we are discussing simulator? What is so important about simulator? So for example, suppose you know what is called LRU replacement policy. So for example, suppose what you did, that you realize that no, LRU is not efficient. Let me propose a new replacement policy. And you have proposed a new replacement policy called my LRU. So how you will convince the people that your proposed LRU is better, your proposed replacement policy is better than LRU? So you have to, there should be some procedure through which you have to show some results based on which the people will convince that, okay, my LRU is better than LRU. So how to do? So when I say better, there are many ways to say better. One is called performance. If you propose a replacement policy like my LRU and it is giving better performance than the LRU, then also you can say, yes, it is better. So performance, there are many parameters to count performance. One is instruction count, then CPI, MPKI, instruction part cycle, average memory access time, network latency. I think all these parameters I have explained in my lecture one. So, and if anything is missed, then also I'll explain in next lectures. But here you just, it is not very important to understand all the parameters, but some of them, for example, MPKI is very important. Is MPKI means miss per kilo instruction. This is a very important parameter. So means if there is a computer, there are two computer likes, one is computer one and computer two. If you are running a same code, same program in both computers. If one computer is giving MPKI 100 and another computer is giving MPKI 50, then 50 is better, right? It is giving less miss. If there are less misses in cache, it means maximum time it is getting hit in cache. So if it is getting hit in cache, it means it is reducing the time. Sometimes we also compare the energy consumption and chip temperature also. Suppose you have proposed a replacement policy which is not improving the performance, but it is reducing the energy consumption and power consumption, or maybe the chip temperature. So this is also possible. that you propose the idea, this idea not improving the performance but improving the power consumption, or maybe hardware overhead, my storage overhead. For example, suppose LRU policy, if you want to implement, for example, suppose it is a hardware overhead or storage overhead required is suppose 1 MB or 1 KB. You have proposed a new replacement policy where it is not improving the performance much, but it is reducing the storage overhead by 50%. Then also you can consider it's a new technique. So sometimes when you propose a new technique, it may either improve performance, energy, and hardware both, all these three, or maybe sometimes it is not improving all these parameter, but some of this parameter it is increasing. So, but basically, what I am saying, it is improving performance or it is reducing energy consumption and all. How we will check it? So that is the main question here. So suppose this is the setup. This is the your processor setup, and in this processor setup, as I said, you have proposed a new replacement policy like my replacement. So how you will check that your replacement is giving better performance or better energy consumption or better hardware overhead? How to combine? So there is two ways. One way is the straightforward way, hardware design. Design two separate processor. One processor based on LRU, another processor you design based on your LRUs, your replacement policy like my LRU. Design complete two separate chip, design two complete separate computer, and then on these two computer run same set of programs, and then check the MPKIs or CPI or the energy consumption. In this way, you can compare that whichever giving less, then it's better. But these type of physical design is not possible, especially for laboratory things, right? Because issue of physical design is lack of facilities in research lab. It is not easy to design a processor, right? And for every small thing, you cannot go and design a processor for every small proposal. Lack of chip fabrication knowledge. Most of you are from CS background, so it is we have very less knowledge in chip fabrication and all. So this is also a disadvantage. Very expensive. If you go for chip designing for all your proposal, it's very expensive and time consuming also. So the alternative is simulator. So what is simulation? Simulation means it's logically designing a computer using programming language C or C++, Java, etc. So it's a software only, but within using this software we can simulate a computer or a part of computer, and most of the simulators are written in C, C++. So the advantage of simulator is it can save your time, easy to implement, only the basic programming knowledge is required, and most of the hardware thing is not required, which is the problem of computer science people. Because yes, we can work on replacement policy, we can work on other parts, but in architecture there are many things. If you want to go for physical design, there are many knowledge from electronics will be required. That is not required here in simulator. You only need to know what is required for computer architecture as a computer science student, and then that will be enough for you to start your simulation. No need to go and understand the low level electronic details of computer and cache memories. And it is cost effective also, and you can go for any kind of design, different types of design. You can test your result because you no need to go for any cheap fabrication thing. So there are two types of simulator exist. One is called full system simulator and one is called trace-based simulator. So full system simulator is the most powerful simulator exist, and we normally recommend people to use full system simulator. So the advantage of full system simulator means it can simulate a complete computer, means including the OS also. It looks like same as a virtual box kind of thing. So if you are using on a full system simulator, so it will, first of all, it will create a virtual machine on your computer, and on at that machine you can install a OS also on that simulator. But the difference between a simulator here and the virtual box is, since it is a simulator, every concept you can code. For example, pipelining, or if you want to change ISA, everything you can code here. You can change the code. You can create any computer using if you are using a full system simulator. So for example, suppose this is your computer host machine, we call it host machine, and you have installed a full system simulator here. So this is your full system simulator which is installed in your computer. So now in this simulator itself will create a simulated computer inside this computer. So this is a simulated computer. So in this simulated computer, you can give any program as an input, and this simulated computer will execute, process it, and give you the output like a normal computer. But this input and output is not just enough. It will, when it is executing your program, it can also record all these parameter like mpki, means instruction count, number of misses, all these things also it will record and give you as a output. That's why full system simulator is very very helpful for computer architecture people. Almost all the researchers use full system simulators, basically who are doing their phds. So this machine, that is simulated machine, is called target machine. This is host machine, this is target machine. So now the next question is how it is possible to simulate a complete computer. So to understand this, I think this slide also I've explained in my lecture one. So in this slide I said that whatever a computer do means that there will be some instruction here in memory. So there will be instruction will be fetched from here to processor, then the instruction will be decoded. After decoding the instruction, we'll go and load this data from memory, and based on this we'll either add it or subtract it. So all these things are logical here, nothing is magic here, right? Everything is logical. Since everything is logical, we can simulate it, and exactly it is doing the same thing. Since everything is logical, we will simulate it. But whenever there will be actual add is required, that add this content of these two, then in this case the arithmetic logic unit of your actual machine, that is the real machine, will be used. So since everything is logical, so we can simulate it, and that's how a full system simulator simulates. But the problem is full system simulators are very very huge, and for a term paper I don't recommend full system simulator because it's very time consuming. You have to spend at least 2 months to understand as a full system simulator completely, and you don't have enough time for all these things in a term paper because this time is limited. So that's why in this course we will not discuss full system simulator, we'll use trace based simulator that I am coming after this slide. So before ending the means going to next slide, I need to explain you something called benchmarks. So if you remember in my first slide, I said that how to compare two computer. I said that okay, if you have proposed a new replacement policy like my replacement, so how you will compare that your replacement is better. So I said that design one computer with LRU, design another computer with my LRU. Now I'll say in simulator design one computer with LRU, and in simulator design another computer with my LRU. So now I am going from physical to design to simulated design, but that is fine. Then I said that run same set of program in this computer one, and run same set of program in computer two, in simulated computer, and then check the performance. So that is fine, but which set of program? If you write your own program, suppose you have written a matrix multiplication program and you are trying to run this matrix multiplication program in both computer and then checking the output, that may not be a correct parameter, because if you write a program, your program may not checking all the parameters that is possible. Maybe the computer has multiple threads, maybe this replacement policy is good for some type of application and maybe it's not good for another kind of application. So the program that you will run may not satisfy all these parameters. So normally what we do to check the performance of two computers, what we normally do, we use some standard written program. These programs are written by some standard groups, and when they have written these programs, they have considered different aspects, right? How many threads will be there? Is it a streaming kind of application, or is there more temporal locality? All these things they consider, and then they have designed this application. So these are called benchmarks. So there are two well-known benchmark groups we use. One is spec benchmarks and one is parsec benchmark. So I think for this Champsim simulator, they will use spec benchmark. So this is what the benchmark. Why benchmark are required? Because if we want to run our own program to check the performance, this program will not check all the parameters. So better to use some standard program written so that we can check all the parameters. So that's why we use benchmark. And what are this spec benchmark? What are there are different application will be there in spec, SL, and parsec. These applications are from various domains. Some of them from maybe from image processing, some of them from machine learning. So what this program will do? There are already data present there, and there is a program. So this in your simulated environment, what it will do? It will just run its program, and when it will running the run the program, it will check all the parameters, because maybe it will use the complete cache. Some of this application may be stream oriented, some of this application may be more on temporal based. So if you run at least 15 16 benchmark from this benchmark suite, then you will understand that okay, okay, this computer is better, because it means that you have tried various type of program on these two computer, and based on various type of testing, this computer is performing better. So that's why this is how we compare. So maybe if I show you a paper here, uh, this is a paper. You can see this is our paper, and all the three authors, including me, of today's workshop are here. Kaushik is here, Prathamesh is here, and also one good point about this paper is an outcome of the last year term paper. Kaushik and Prathamesh proposed this concept in their last term paper, and they finished this paper by the summer, because they have some problem with simulator, so then they completed it in summer, and we published it recently in date. So if you see this paper, after this proposal, here they have compared their proposed replacement policy with different other existing replacement policies. So how they have compared it, and you can see there are different types of mixes here, W1, W2. These are the benchmark programs. So what they did, they have implemented their own a proposal in Champsim, as well as they have proposed some other existing technique also in Champsim, and one by one in all these techniques, they have run these benchmarks, these programs, and they have compared the results. Means what is the miss rate for array, what is the miss rate for EAF, what is the miss rate for this technique. In this way, they have recorded all these misses, put it in Excel sheet, and then compared it, and then created a graph. So all these things are required for term paper, as well as if you write any kind of research paper, this will be required. So I hope you understand the importance of a simulator. So I am not explaining you the simulator. I am just trying to explain you the importance of a simulator. So I hope what is benchmarks I have explained you properly. Then these slides I'm skipping, because these are for a full system simulator called GEM5, very widely used, very popular, very much powerful, but not good for your term paper, because it will spend a lot of your time to understand it. If you will do further research, if you are doing PhD, then I'll encourage you to understand this simulator, because if you are doing PhD, then yes, sometimes trace-based simulator will not be enough. At some time, anyhow, you have to start a full system simulator. So GEM5 is a very powerful full system simulator, but I'm skipping it. So I'm starting with trace-based simulator. So trace-based simulator means, first I have to explain what is called trace. So trace means many things we can call trace. One is the request made by code. Suppose you are running an application in this code C1. If you are running an application in this code C1, then this code will request for data, because as I have explained in my first class, that computer systems are based on von Neumann architecture. Initially, everything is in memory. And if you are running an application in code, then one by one the data and instruction will be fetched from memory, and core will execute it, and the result will be written back to the memory. So communication between core and memory is based on load and store, right? So trace means what will happen, suppose you will run this thing in a full system simulator first of all, and in full system simulator, in this core you will run an application, and then whatever this core is requesting, means it will request for either load or store. If it want to fetch something from memory, it will go for load request for address, and if it wants to write, this core want to write something to address, then it will go for store request for this address. So load and store request, maybe this is first time this core will request for a load on this address, maybe it will go for another load on this address, then it will maybe go for store on this address. And so what we'll do, if we are running it in full system simulator, we can record these traces, that okay, core 1 first requested for a load of this address, then core 1 requested for a load for this address, then it is requested for a store for this address. So all this thing you can record here in a file, and that is called your trace file. So trace file can be is generated running all the bench. For example, suppose you are using spec benchmark. So spec benchmark has many applications. So as I have shown here, our paper, there were many applications like W1, W2, W3. So what we need to do is we have to run those benchmark first of all in a full system simulator, and then collect the traces like this, and then use this trace in a trace-based simulator. But to make your life simple, you no need to use any full system simulator, because these kind of traces are already available. So for all the benchmarks that I've shown, spec benchmarks, their traces are already there. Someone has already run it on a full system simulator, and they have recorded the traces for you, and these traces are already available. You just use these traces. Now the next question is, if you have trace, then how you can design a simulator, and what is a trace-based simulator? So before going to any existing trace based simulator, here I am trying to explain you how you can write your own trace based simulator. Maybe it will not enough for your term paper because your written simulator cannot cover every aspect. But if there is a requirement, like only calculate the number of misses, then you can write your own simulator. How? Suppose this is a cache memory, set associative cache, and this is the trace. So, and if I say that, okay, this is the trace, so cache is, core is requesting these addresses in this sequence. So find out the number of misses of the cache. What you will do, first of all, you know the behavior of set associative cache. Behavior of set associative cache is you have to find out the set index. So this is the address in hexadecimal format. So from this address, you will find the set index first of all, and you'll find the set index, and then you'll place, for example, suppose assume that all these are mapping to this set, first set. So you'll store it in here. Then you'll go here, you'll find the set index, you'll store it in here. Then you'll go here and you'll store it in here. And then when you'll go here, you'll store it in here. So after executing all these four traces, your set one will be full. Now again, if your trace is long and there will be one more address here which is mapping to set one, then your set one is full. Then you have to apply your replacement policy here. So that will be a miss. Or suppose after some time you are again requesting for this block, and this block is already in cache, so this will be a hit. So hit and miss, whatever I'm saying here, this is a very simple logic, and you can easily write a C or C++ program to handle this. And your program will give the output of number of misses and number of hits. You only need to give input as this trace. If you give a trace file to your program, I think it can easily simulate all this thing, and it will give you number of hit and number of miss. This is also a simulator. That means you have designed your own simulator. But the problem with your own simulator is it cannot handle many other things. There will be many different possibilities and many other things that may not be possible. And also, your proposed simulator is not widely accepted. So if you use your term paper using your own simulator, and then you want to publish your results, people will say that first of all, show us your code of your simulator, how you have simulated, because it is not widely accepted yet. So that's why what we will do, we will use some well-known simulator which is widely used by the different groups of computer architecture, so that no one will question your implementation and your result comparison. So some of the well-known trace-based simulators are, I think here, BookSim is for network on chip simulator. DRAM Sim 2 is for DRAM simulator. If any one of you are using or will work on main memory, then DRAM Sim 2 is required. I think next week someone will present basic introduction about DRAM Sim 2. Noxim is also an NFC simulator, and Champsim, that is a simulator that today we will discuss. Champsim is a trace-based simulator again. Now I think you know what is called trace-based simulator, but Champsim is mainly used for cache memories. So anything like Champsim is mainly used for there is a prefetching championship organized by a group every year, and that in that prefetching championship they use this simulator called Champsim mainly for prefetching. But last year we have found that this Champsim can be used for other cache memory operation also. For example, replacement policy and this cache partitioning and all these things we can also use Champsim. It says code base is small and it is easy to work. So that's why we have decided this time that if you guys are working on cache memory, go for Champsim. And if you want to use propose something on main memory, then you will go for DRAM Sim 2. So this week we are discussing Champsim. Next week we will discuss DRAM Sim 2. So I think I'll not discuss anything more. That is enough from my side. The rest of the things will be handled by Kaushik and Prathamesh, because I am not the expert of Champsim. Honestly speaking, I never use Champsim also. I don't know even how to run, because I normally work on Champ 5. So if you have any doubt, you clear it today. And if during the term paper also, if you face any problem on Champsim, you can contact them instead of contacting me, because honestly, I never use Champsim and I don't have any experience on Champsim. If you, any of you have some experience on, if you want to take risk and want to work on Champ 5, then you can ask me. But that will be a very risky thing for term paper. So I'll stop here. This is not ending here. There are many other slides, so I'm not continuing other slides. I'm stopping here and then over to, I think, Prathamesh and Kaushik. And if you have any question before starting, you can ask.
Okay, fine, sir. Yeah, okay. So, hi everyone, good evening. So, let's start this tutorial session. I hope I'm audible, right?
Yes, sir.
Yeah.
Yes, sir.
Okay. So let me start presenting. Uh, I hope. So how many of you have downloaded the Champsim and unzipped it? Okay. So most of you have, right? Is my screen visible?
Yes, sir.
Yes, sir.
Yeah. Yeah. Okay. So see. So this is what you might be having, right? After unzipping the folder, right? So let's start to the basics. So how many you have got that this file, right? Let me one second. Right. So I request everyone to please go to this DPC3 traces Dropbox. Okay. You go to this site. Okay. And in this site you can download any of the trace, right? But I will show you. You download this GCC, this GCC 13B trace. Okay. So are you doing it? Actually, this will be a much more interactive session.
Yes, sir.
Yeah. So you can leave your mic open also. There is no problem. Everyone is able to access this, right?
Yes, sir.
Yeah. Okay.
Yes.
Yeah. So just download this GCC, right? Any of the GCC file, right? You can download it from here. Right. So I have already downloaded it. Okay. So most of you have put it for download, right?
Yes, sir.
Downloaded, sir.
Downloaded? Yeah, fine. Okay. So you know what you have to do. Just a minute. Yeah. So what you have to do after downloading it, you have to see you have to create a folder in this Champsim, right? And you name that folder the DPC3 underscore traces.
Sir, there is already one folder
Yeah. So
with the
okay. So
same name.
if that folder is already there, you go inside that folder and you put that file there.
After extracting that
No, no,
file,
no. You don't
sorry.
have to extract. See, you don't
Okay,
have to
sir. Okay,
extract it.
okay.
Yeah. You don't have to extract it. See, these are the trace file. Okay. So I will explain you everything once. I want everyone to just complete the basic setup. Yeah. So perhaps you can let me know when everyone is done. Putting that compressed file in the DPC3 traces folder. Actually, this will be a much more hands-on session, so that you will be getting an idea of how a simulation works, and how to get results, how to get some meaning out of the results. So I hope this will be much more interactive. Done? Okay. So some of you have done. So yeah. Okay. Thank you. So what now next you have to do is, in the same folder, right? Means in the Champsim folder, where every folder is present, you have to open the terminal, right? And in terminal, what we have to do is, we have to build it. Right now let me explain you what is there here. Right, so you go into this readme file. Please open the readme.md file. Right, have you opened?
Yes, sir.
Okay. Yeah, so see here what is there. So this is the command for building the Champsim, right? So building means, so now let me explain you what exactly we mean by simulator. So now if for example, let's take a very small example. Let's say you have to build your own replacement policy, right? So in order to build your own replacement policy, this will actually be a hardware structure, right? So it will be implemented in a chip. But how we would know it beforehand, that what we are proposing is actually get some performance improvement, or energy reduction, or something like that. So we have to do simulation runs on it. So when we are doing the simulations, we have the Champsim, that is the simulator is already built in such a way that all the basics and previous state of the art policies are already mentioned there, right? So now when we are building the simulator, what we are passing is, right, so these are the parameters. In the line number 18 you can see, so dot slash build champsim.sh, the first parameter, which is bimodal, is actually a branch predictor, right? So this is an inbuilt branch predictor which is mentioned in the Champsim. We will go to the folder also, but here we are using this bimodal. There are many branch predictors, but we are using bimodal one, right? Now this you can see in the command, there are these 4 no, right? So what do you mean by this no? So this parameters is actually L1 prefetcher, right? So in the hardware we use something which is known as prefetcher, to hide the latency, right? So we are implementing here entire cache hierarchy, and we are using here 3 levels of cache, right? So first level is split, that is L1 instruction and L1 data. So we are not using, no means not using predictor prefetcher at L1, not using prefetcher at L1 data, right? Not in neither in instruction nor in data. The second is L2 prefetcher, right? You can see here L2 prefetcher is also off, and the last level cache prefetcher is also off, right? And the replacement policy, here you can see this LRU. This LRU is the replacement policy which we are using at the last level cache, and we are simulating it for 1 core, right? So what you do is, you copy this command, right? You copy this command and you run it on the terminal, right? And let me know what you are getting. Are you getting something?
Permission denied.
Yeah. So if you are getting that permission denied thing now, then please go to this doc file which I have shared with you. Actually there is some problem for me sharing, so I have to switch the tab every time. Yeah, so here you can see those who are getting these errors, probably you can run these 2 commands, right? So you are getting errors in this build champsim.sh, right? So you can come here. Sorry. Right. So you do these two things. One thing is this chmod plus x build champsim.sh, and the second thing is this sed minus I minus e, this thing build champsim.sh. You copy these things and you run it on the terminal. Then let's see what happens.
Yes, sir. Now it's compiling.
Yeah.
So
Okay.
Champsim build failed.
Champsim build failed.
Yes.
For everyone, are you getting that?
Sir, there are some warnings which say that if
No, no. Warning is fine. Warning is fine.
okay,
Warning is fine. What I am saying is, are you able to get this thing?
yes, sir.
No, sir.
Oh, I think probably most of the students are getting it. Who is not getting it? Can they say? Yeah, Anshu. What is your problem? Aditya also not getting it. What is the error, Anshu?
Sir, command not found and Champsim build failed.
A command not found.
Yes,
So
sir.
so like what are you doing there?
Sir, after running both the two commands which I copied, sir,
Hmm.
again I this build Champsim dot by model.
Hmm.
This command I uh,
There might be some issue on your local machine, I guess. Then rest everyone, you are getting it right.
Yes, sir.
Okay. So Anshu, we will try to figure it out later, perhaps, right? I will
okay,
carry
sir.
on with the tutorial, right? If you have any doubts, we can personally solve it, right?
Okay, sir.
Yeah. Okay. So once you have done this, build. So what is happening is you can see this. All the parameters are set, right? Now you have to run it, right? So for run, you can again go there and take the parameters. I have already there in the file. I have already shared with you the command for run. So you can just copy paste it, right? So so you put it on run.
So it is again showing permission denied.
Yeah. So again you have to give these two permissions, right? For dot slash for run underscore champsim.sh, you have to give all both the conditions, the chmod thing and that sed thing.
Okay, sir.
Yeah. Just let me know, once when you have put it for run, right? So the build. So let me show the build file for run, right? Sorry, the readme file for run, right? So this is the readme file, right? So for running the experiments, what we need is this is the sample trace, right? So what is the binary? So the binary means whichever output which came after building it, right? So dot slash run champsim.sh, the binary is the output which we got after running after building the code. Then this is n warm, right? So what it is? It is number of warm up instructions. So basically what we do, we warm up the caches, right? Because initially everything will be empty, right? So this warming up is needed so that whenever you are running the actual experiments, the cache should not be empty, right? So this is number of warm up instructions. So the number of warm up instructions here we are giving as 1 million. Everything here is in million, right? Then there is nsim, which is the number of simulation instructions, right? So in our running which we are giving 10, so 10 million instructions we are simulating, and this trace is the trace which we downloaded from that dpc3 box, right? That gcc1. So this is the way you give it for run. Yeah, blinking cursor means it is running. Blinking cursor means it is running. So what error you are getting?
Sir, permission denied.
Uh, so you have to give that both the permissions. You
Sir,
gave it?
yes, sir. After that also.
Uh, that should not happen. Yeah, so the output is let me address your permission denied thing in later, okay, Shekhar?
Okay, sir.
Yeah, Tawkir has given it chmod plus x. You can probably do that. Yeah, okay. So what will happen is, let me tell you what will happen, right? So when you run it, first of all, let me know how many of you completed the run. Yeah, any questions? Yeah, Tawkir has completed. Upasna, you have also completed. Navneet has also completed.
Completed, sir.
Okay, you have also completed. Anyone there still who is pending? Yeah. So you will be seeing that wait a minute, this is before the run. Yeah, so you will see this result underscore tell million one folder is generated. Are you able to see that folder?
Yes, sir.
Yeah, please go in that folder. That is the output file which is generated, and click on that text file. Are you able to see a file like this?
Yes, sir.
Yeah. Okay, Navneet is able to see your Upasna. You are getting the file? Yes. Okay. Rohit? Yeah. Okay. Yeah. Okay. So see, we will sort out that error thing later. So here you can see, this is how the output file is printed, right? So here it will give, what was the specification you gave, right? So number of warm up instructions here, 1 million, right? For 10 million we simulated it. Yeah. So right, the number of CPU is 1, right? And I will come to how we set this LLC set and LLC way, right? So here is the basic thing. Now here is most important thing is this. This is the region of interest, right? So what actually we got by running this trace? So you can see this CPU 0, right? So for CPU 0, you got the IPC, right? So CPU 0 means we are actually running for only one core. In multi-core scenario, these things will change, right? So for one core, what is happening is, the IPC, that is instructions per cycle, for this entire trace, right? This GCC trace which we ran is 0.199, right? So this is the instructions per cycle, right? Then we can get all the details here. This is L1D total accesses, right? So we are interested normally when we are working at last level cache, right? This simulation results, right? From here you can see, right? So here you can see, what is the total accesses to the last level cache, how many were hits, how many were miss, right? So basically this will give you an idea. Suppose you have implemented your own replacement policy, right? Then you compare these results with the previous replacement policies. Then you find out that, okay, my IPC is improving, right? So the number of hits, let's say, if we look at the last level cache total access, if in this policy we are getting this many hits, right? So we can say that our policy is, better in terms of hit rate. You are getting it? So this is how, we do this. So there's a lot more to explain in the simulator, but this is how the basic things work. Are you able to get it?
Yes, sir.
Okay, so this is how, this is the output file which will be generated. Now, let's look at the simulator code, right? So let's see how they are doing on a very high level. So are you able to see these folders, right, in the Champsim simulator? So you can see this replacement folder. Please open that replacement folder. Right? Is everyone there?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So you see there is this LRU policy, right? You open that LRU thing. Everybody opened it?
Yes, sir.
Yeah. So see, this LRU. So you know the working of the LRU policy, right? So how does the LRU work? Can anyone explain like how it is implemented? Okay,
So
so yeah. So basically, what we are doing is we are simulating its behavior in C++, right? Insertion at MRU and eviction from LRU. Yeah, that is true. But yeah. So what is there is in the code? What is there is there are two main functions, right? If you are looking at replacement policy, so there is one function which is known as find victim, right? So can anyone tell me when this function will be used, this find victim?
So when the size of the block is full.
Size of the block or size of the set?
Cache.
Yeah, cache, right? Yeah, for eviction, right? So when that particular set, right, when that particular set is full and we have to replace something, then this find victim function is used, right? So this function you have to change whenever you are proposing some new replacement policy, right? And now let's say this is the update replacement state, right? So update replacement state means let me explain you better with the SRIP. So how many of you have gone through that SRRIP paper? Yeah, Upasna. Okay, Tawkir has also gone. Okay, so let's everyone, let's do some practical hands-on thing, right? So that you also get some experience here. So uh, so please come to this SRRIP code. You open it from the replacement, right? And let me know when you all have opened the SRRIP code. Opened it? Okay. SRRIP opened. Okay, fine. Now come to this LLC find victim function, right? Now at a upper level, right, how a victim is calculated, right? So we have to so can anyone briefly explain me what is the logic of SRRIP, how it finds the victim? Anyone?
based on a high bit number.
Yeah, high RRIP value, right? The high RRPV value.
RRPV value. Yes, sir.
Yeah, with longest dereference interval. Yeah, right, Tokir. Yeah, so their algorithm is basically what? Whatever is the longest RRPV line, they evict it, right? And for this example, they have considered RRPV equal to 3 as highest. Okay, for 2 bit for 2 bit counters, right? So let's see how how in a simulator that is implemented, right? So let's say we get a call to this LLC find victim function, right? So from where the call is coming, I will explain later. So you can see here, while one. Okay, so here is a while one. So what is the objective of this code? To look for the maximum RRPV, right? So what this will do is, it in the for loop what they are doing is, from I equal to 0 to I less than LLC way, right? So they are in that particular set, right? If in that particular set they are checking which way is equal to maximum RRPV, right? And if that way is equal to maximum RRPV, that is our eviction candidate, right? So they are returning that way, right? So what this for loop is doing is, it is simply searching for a way whose RRPV value is equal to maximum RRPV, and if it's found one, then it returns the index, right? It returns that way. So that is our victim, as simple as that, for find victim, right? If we come out of this for loop, which means what happens, can anyone explain me what happens when we come out of this for loop?
You don't find any maximum.
Yeah, so we don't find a way which is equal to maximum way, right? So what the algorithm says, then it will increment the RRPV of all the ways, right? So this is the algorithm of SRRIP. When we don't find any way with maximum RRPV, we have to evict something, right? So it will increment. It will increment in the line number 29. You can see it will increment, the RRPV of all the ways, and again the while loop will, take. So again it will be, so let's say if any way has RRPV equal to 2, so it will increase to 3, and then again this while one will happen, and then it will again increase to 3. Now this will be acting as a victim, right? So this is a very simple example of how a find victim function is implemented in the simulator, right? You are able to get it?
Yes, sir.
Yeah. Now, can anyone explain what happens on an NLC hit? So you come to this update replacement function, right? And you come at the very bottom. Look at this line number 64. In the same SRRIP code, you come to this LLC update replacement function, and you come to line number 64, right? So what happens, let's say we are at last level cache, we are looking for a block and there is a hit. So what the policy says, it says that you put that, keep the RRIP value to be 0, right? So whatever was the RRP value, you keep it as 0, or else you keep it as, maximum minus 1, right? So what I request you everyone is, first run for the same SRRIP code, just change the replacement poly to SRRIP. So let me show you how it is done, right? So you clear this, right? So you again build it. Okay, /build underscore champsim dot sh. You can do it with me also, right? Together by model. So this is the branch predictor. Then 4 nodes, right? Now in the earlier what we wrote the replacement policy was LRU, right? So here you write SRRIP, just that, and then you give number of cores, that is 1. So /build champsim.sh by model 4 nodes SRRIP 1, right? Just instead of LRU you replace it with SRRIP, and then build it. Just let me know when you are finished building. Okay, Navneet done, Bhasna done, Rohit done. Unyan also build it. Rest everyone, are you able to follow? Done. Okay, Shivam also done. Right. So you again, you run it and just make sure, you use the binary. So what is the this for run? So let me do it organically. So it is dot slash run underscore champsim dot sh, right? You can probably go into the history and change this, right? So you can copy this binary thing. Right. So for then what you have to give? We have to give the number of simulation instructions for for warm up. So we are giving it again 1 million, then space, then we are simulating it for 10 million, right? So 10, and then you have to give the name of the trace, right? So we are giving GCC underscore 13B, the same trace. Right? Then you go for run. Right? Just make sure that the binary which you are giving there, that is that bimodal part, you give it the latest one. That is the SRRIP-1 core 1, right? And rest all the parameter remains the same. Let's see what is the effect of replacement policy, right? So you put the code for running. Okay, Upasna, yes. Navneet, okay, done. Unyan also done. Okay, Rohit also done. Right. So let's go to that folder. You will see one more file will be generated there. Right. You come to this results underscore 10 million folder. You see one more file is generated, right? Which is named as no GCC1 and with SRRIP1 core. Right. So you open that file too. Right. So let's see let's compare what are the results of this two file. Right. So probably what we can do is now actually this will cause some conflict. So this LRU, you just simply rename it as LRU so that there is no confusion. So just rename it as LRU something, right? LRU underscore results, and you rename the other file which is considering SRRIP with SRRIP results. So we can compare the results. Right. So now let's see what are the results, right? Comparison between results. Okay, right. So this is the LRU results, right? In LRU, what we got IPC was 0.199591, right? Now let's see what is the results in SRRIP, right? Because we just changed, yeah. So here the result is 0.198. So which is better, LRU or SRRIP? Yeah, LRU. So for this particular trace, yeah, so for this particular trace, which is the GCC on a single core setting, when we are warming up the caches for 1 million instructions and executing for 10 million instructions, LRU is actually performing better than SRRIP. Right? This might change also, right? There is no big deal. So let's let's try to do one more thing. Instead of running it for 10 million, just run it for 20 million and see. Let's see what are the results. Let's try to run it for 20 million, right? So no need to build again because we have actually built it. Just go to the history part and instead of that 10, you make it 20. Yeah, okay, I will explain. So for 20 million you put it and you set it for run. Yeah, Tokir, you have any specific problem, like specific question? Hello, Tokir? How to compare the results? Yeah, I will explain you. I will explain you. See, in the in the comparison part, when we come to LRU, right, we can look at many of the parameters here. But basically, what we look is when we come to this region of interest, right? In this region of interest, 1 minute. So you can look at this line number, right, 21. Here you can see the region of interest. You can see IPC, cumulative IPC, right? In LRU it was 0.199, right? IPC is instructions per cycle. So and in SRRIP, what we got is IPC is 0.198. So it is 198 here and it is 199 here, right? So actually LRU is able to run more instructions per cycle as compared to SRRIP for this particular trace. Is your doubt clear, Tawkir? Yeah, okay. Yeah, so is anyone done with, for 20 million? Yeah, okay. So Rohit, you can explain what different results you found for 20 million?
Sir, the IPC has increased to 0.2045
In SRRIP, right?
in SRRIP 20 million instructions.
Yeah, so you are comparing it with SRRIP 10 million, right?
Yes, sir.
Yeah, 0.2045, right?
Yes, sir.
Yeah, so here you can see for 20 million. So it also depends, right? So can you explain, like, can you give some insight why this happens? Like for 20 million, the results are improving, or it's at least we can say it's changing, right?
Yes, sir.
Yeah, so what could be probable reason?
So I haven't looked into SRRIP that much, that paper. So
Yeah, no. I'm not asking
yeah.
specifically regarding SRRIP, but just
Mm-hmm.
in general, why do you think results are changing when we are, changing the number of simulated instructions? Just a wild guess, maybe. It has something to do with
Maybe
the trace.
like, sir, as the instructions keep on increasing, our IPC will also increase like that.
No, not in that way. See, what we are doing is this trace, this GCC trace which we are running, this is actually a trace of, a C compiler. How a C compiler actually generates the memory references, right? When what exactly we mean by trace is actually it is a program. In actual machine, what will happen? If we are double clicking on a file, it will actually go and reference memory, right?
Yes, yes.
Yeah, so this is that GCC trace is a sampled trace of how the compiler works. So the compiler will go into the memory, right? It will touch some addresses, it will bring that blocks in cache, right? So actually it is storing that pattern, right? So when that trace is expanded, so what do you mean by 10 million instructions is that trace we are taking and we are just sampling that 10 million instructions and putting it. So probably what is happening is we are not able to get the real nature of that program, right? So if we increase the number of simulation instructions, we get the actual whole picture, right?
Okay, got it, sir. So, sir, it's like, until a certain number of instructions, let's say like 30, 40 million, it will keep on increasing and then it will like have diminishing returns like that.
Yeah, then it's kind of it saturates.
Okay, got it, sir.
Yeah, when it saturates, now you will get to know that okay, now I am getting exact, so for research purposes, what is good, right? They will actually go to 200 million instructions per core.
Okay, okay.
right? So we have done it for 10 million. They will actually do it for 200 million instructions at least for per core. Fine. So are everyone also done with the 20 million thing? They also got the same results?
Yes, sir.
Yeah. Okay. Okay. Fine. Now, let's do one thing, right? That SRRIP code which we implemented now, let's try to change some things there, right? Now, everyone, please come to that SRRIP code and come to this line number 64. Is everyone there?
Yes, sir.
Okay. So what it is doing is, this is the update replacement function. Okay. This is the update replacement, and on every cache hit, right? On every cache hit, what it is doing, it is setting the RRBV value of that way to be 0, right? So let's just do one thing. Instead of this 0, right? What you make is, you set this RRPV value equal to 2, right? Let's just save it. Do Control S, right? And again try to do it for 20 million, the SRRIP thing, and let's see what is the difference here. On every hit, just make sure instead of that 0 you assign it 2 value, right? Just save it, and again build it. Now you have to build it again because you have changed the code. So let me show you what we have to do. Save it, right? And you build it for SRRIP, right? So this will be the command, build Champsim SRRIP1, right? You build it and again you run for 20 million, and then let me know what difference you found in the results. Actually the file might be overwritten also, but yeah, that might be overwritten if you have not renamed it. So probably you can first rename the 20 million results file, or it will be overwritten. So rest, are you Anshu? You are still getting that error, is it?
Yes, sir.
Okay. What is the error actually? After giving all the permissions, still it is there.
Yes, sir. Champsim build failed, sir. The first command is not working.
Oh. Okay. Okay, we will sort that thing out. Okay, then Ashish, you are able to get it? And how many? Okay, so Rahul, you are able to get it?
No, sir, same problem.
Oh, during the build phase only you are getting the error.
Sir, in the output file, I am not getting the full output. It's showing only 13 line only, and showing Champsim does not support trace other than GZ or XZ compression.
Yeah. So what you gave there then?
Sir, same what you have done, I have done the same.
Oh, but we are giving the trace in the .gz or xz file only, right? Here you can see.
Yeah, I have done the same only, but I am not. I don't know why it's showing like this.
Okay, so perhaps we can take a separate session, right? For those who are getting errors, we can resolve it. Okay.
Okay, okay, sir.
Yeah, we will take this. Yeah. So anyone got the results for the 20 million?
So
Rohit,
it
Upasna.
it has reduced actually IPC. It's 0.204164 right now.
Yeah, it's reduced, right?
Yes, sir.
Yeah. So why is that reduced? Because on every hit we were actually promoting that block to RRPV equal to 0, right?
Yes, sir.
Earlier. So just
earlier.
to clarify things, RRPV equal to 0 means we are classifying that block as a cache friendly block, right? So it will stay in the cache for longer time.
Oh, yes, got it,
Yeah,
sir.
and RRPV equal to 3. 3 means it is very near to eviction. As soon as we found that there is no space, we will just kick out the block which is having maximum RRP equal to 3, right?
Yes, sir.
Yeah, so now as we have set the RRP equal to 2, actually we have classified that particular block as a, more towards not so cache friendly block. So it might get evicted. So before it can get some hits, it is evicted. So that's why we see decline in IPC.
Yes, sir.
Yeah. Anyone else who got the results? Navneet, you got the results? There seems to be some problem with your audio. Okay, Upasna, it's still running. What about else? Aditya Singh Gangwar, you are also facing the error. Shivam, you got the results?
No, sir, it is showing permission denied in running phase.
In the running phase.
Yes, sir.
Oh.
After building, when I run running part, it is showing permission denied.
Okay. But I think we can still, you have given the permission for run also.
Yes,
chmod plus x run champsim.sh.
yes, sir, sir. Both. I have given both.
Okay. Okay. Okay, we can look into that.
Okay, sir.
Tawkir sir, we are setting 2 means it is evicting faster. Yeah, it is evicting faster, right? Right. It is giving less chance for it to stay in cache. Right, Tawkir. Unnayan is yeah, IPC decreased 0.204, right? So IPC is decreased, right? So this is how you have to make the changes for your own replacement and all, right? So it's already 50 minutes, and I think I don't want to go much in detail, but let me give you a brief what it does. So everyone, please come to this inc file. This is the include folder, right? So just let me know when everyone is in the include folder. Okay, and then Rohit, Upasna, navigated to INC. Right. So see in this INC folder, right, there are many of the header files. So in the header files, what you have to do is there are many which are of use, but primarily if you are looking, just to begin, open this cache.h file, right? Right. Just open this cache.h file, and navigate to last level cache, right, which is line number 72, right? Let me know once you are there. Line number 72 at cache.h. Okay. Yeah. Okay. Fine. So at line number 72 na, you come down. Line number 73, you can see hash define LLC set, right? That is number of CPU into 2048, right? So here in the simulation we are giving number of CPUs as 1, right? So there we are giving 1. So LLC sets will be 2048, right? And the LLC way we are giving here as 16, and the block is mentioned in champsim.h, right? The block size is 64 bytes. So can you give me what is the cache size which we are simulating here? Number of sets is 2048, number of ways is 16, and the block size is 64. So what will be the size of last level cache? 32 MB. How, Rohit? Can you explain? 32 KB. No.
Sir, like 2048 sets are there, and
Right.
each of them are like 2 power 4, so 2 power 15 blocks will be there. Sorry.
Yeah. Block size is 64 bytes.
Okay, in that case, 2 power, it will be 2 MB, right, sir?
Right. 2 MB.
Yeah.
Yeah. Yeah. So whatever experiments we have done, na, we have kept this cache.h file as it is, right? So let's say you have to see, right, what is the results for 4 MB, right? That is like cache sizes increase, right? So what we will do, instead of 2048, make this 4096 and again run it for 20 million, right? So instead of this 2048, make it 4096. Then what would be the cache capacity? Just save it, Control S. So have you done it? 4096, everyone? This means now from 2 MB we have increased to 4 MB, right? Yeah. So now for 4 MB, you just save this file in cache.h and again build it and again run it. So build srrip, right? And again run it for 20 million, right? If you are not renaming it now, then the folder will be overlapped. So it's better to rename the folder after every instruction, every execution. So again run for 20 million, and now let me know what is the difference you found. Okay. Yeah, so for those who are not able to run it, when can we keep the this doubt session? Can you give me some in the near future only? Perhaps tomorrow, is it possible for you? Those who are not able to.
Yes, sir.
Okay,
Yes, sir, it's
tomorrow.
fine.
Okay, tomorrow it's fine, na? Tomorrow at what
Sir,
time?
tomorrow time, yeah.
Okay.
This time only.
6 p.m. is okay, sir, I
Yes, sir, 6 p.m.
6 p.m. Okay, sir, 6 p.m.
Yes, sir, 6
Okay.
p.m. is fine.
Okay. Then tomorrow 6 p.m. we will have doubt class. Okay. We will resolve your issues. Fine.
Sir, please upload the recorded video.
Yeah, yeah, yeah. This Dr. Shirshendu will upload it. Yeah. So those who are still getting it run, are you done with the run? It's running. Okay. What is 4 number? Where it is 4? Actually, if yeah, that is for 4 core. That is actually I was trying to also explain you for, yeah, number 4 means it is for 4 core. No, 4 no. Okay, 4 no you are asking. Okay, that no is na, yeah. Let me come here. That no is na, actually we are disabling all the prefetchers. Let me show you. So the argument for you can see the readme file at your own leisure, right? You can see it. You have to play with this simulator for a long time, so you can uh, play with this. So here you can see in the readme file, na, when we are giving these parameters, dot slash build dot sh, right? The first no is that we are disabling the L1 instruction prefetcher. The second no is we are disabling the L1 data prefetcher. Third no is we are disabling L2 prefetcher, and the fourth no is we are disabling the LLC prefetcher. Here it is there in the readme file, right? Is your doubt clarified? Okay. Why we are disabling it now? The reason is we are just curious to know what is the impact of this replacement policy, right? instead of that no, you can see, let me show you, right? So instead of that no, what you can do is in Champsim, main Champsim folder, you can see just like replacement, there is also one prefetcher folder. So you go into this prefetcher, and there are many prefetchers, right? So let's see, there is this L1 LLC. See, this is where it is. Yeah, this is llc prefetcher.cc, right? So instead of that fourth no, you can write this llc underscore prefetcher. So that will give you your results when the llc is active with prefetcher also. Yeah, Upasna IPC is increased by how much? Can you tell us?
Okay, so earlier it was 0.204164. Now
Right.
it's 0.210756.
Right. So when we are increasing the cache size, IPC is increasing, right? So anyone, just can you, perhaps someone else who can answer this, why it is increasing?
So more blocks, so obviously we can retain more data, right? So
All right. So cache capacity is, last level cache is more, that means there will be less conflict misses, right?
yes,
We
sir.
can retain more. So there will be not much evictions, right? So that this is how you can play with this, right? So the bottom line is, what this session was, just to make you quite comfortable with this simulation infrastructure. So if it is necessary now, we can take one more live session. It's not a problem from my side, but just make sure that you play with this. So similarly, if you read the readme file now, you can get the command for running it on multi-core, right? So perhaps if you are fine, we can tomorrow, or we can take one more session if you want. It's entirely up to you. So the goal is just to make you comfortable, and perhaps let me explain at the brief what it is doing. So you can read the readme file for multi-core setup, right? So basically what you are doing is, if someone is working on replacement, right? So in the replacement, what you have to do is, you have to just create your own replacement file and just give your name there for running, right? So that is bimodal dot slash build bimodal underscore sorry build underscore champsim dot sh, right? No, and then we give LRU, right? So instead of LRU, you make your own file here and give the name of your own file, right? So you open the code, right? Just like SRRIP we did, right? So you open the code and try to understand, right? And one more important point which I have not covered here. So this one point was this include, right? In this there was this cache.h. So similarly, let me explain you quickly what is this block.h, right? So this block.h is, you might be remembering, with every block, we are having every field, right? This is the valid bit, right? There is the prefetch bit, there is a dirty bit, right? Whenever we are evicting something, we check whether the bit is dirty or not, right? So if similarly, for if you are proposing your own technique, and if you require some bits to be sent along with the block, so you can change here in the block.h file, right? So similarly, there is this this is the fair. And most importantly, what I would like to share with you is, everyone please open this source file, src file in the Champsim folder. Src file, you open it and let me know when you are in the src file. Right? Is everyone on the src file? Yeah, okay. So what is most important for you, as this simulator is mainly for cache, so you open this cache.cc file, right? Now this is your main file. Actually, if you are proposing something now, even if you are proposing any new replacement policy, right, the code will come from here, right? So there are different type there, control F and see this operate, type operate, right? And go to the last one, right? You will come to line number 1045, right? Let me know when you are there. Are you at the operate function? Yeah, okay. So see, here is the most important thing, right? In the operate function, this is all called handle fill, right? So handle write back, handle read, right? So what happens on a read, what happens on a fill, right? So this is the main source code of the this right. So as you saw in this srrip file, right? When we come to this srrip file, we got to know these two functions, right? The first one was find victim function, right? This find victim function, and other was this update replacement state, right? So from where it is called? It is called from here. You go to this cache.cc. In the cache.cc, just do control F and you give there find underscore victim, right? You give there find underscore victim. You can see this function is called from here. Are you able to get this? Right? So this is the main code, this cache.cc. But what my advice for you would be, first just try to play around with the basics of the simulator, right? Try to get your good hand on it, and then when you are actually trying to what you are trying to implement your proposal, at that time you come here, and basically there will be one assignment coming to you, which will be just slight modification in the actual code, right? One assignment will be coming to you. In that, you just have to slightly modify this code and see what are the results you are getting, right? So this is basically, and most importantly, you should be able to guess like why this is happening, right? So just like we our intuition should be matching with the results which we are getting. So similarly, we expanded the cache size from 2 MB to 4 MB, right? So what will happen is, if that particular application is cache friendly, then it will certainly benefit from extra cache space. But let's say the nature of the application is not so cache friendly. So even if you give in 4 MB or 8 MB, the IPC will remain same. You are getting it? So IPC will not fluctuate more if the application is not having that much demand in the cache itself. So you can try to play with this, and I am stopping my recording for now. If you have any questions, we can take it. No, recording is still on. I am stopping this sharing.